Okay, so I have a fresh piece of paper, and so so I'm just going to kind of do some complements of this thing. So other facts. And kind of tell you the way that I like to think about this. So so if X is locally compact, right? So if X is locally compact, what have we shown? Well, we've shown that we have kind of a correspondence between maps from a topological space to the mapping space and maps from the product to here. Okay, so this goes from F in two variables to this map to maps. F hat here. Okay, so this takes a T and it sends it to here. Okay, so in fancy terminology, right? The functors here we have two functors. So the functor here, if I take X and then I take its product with something, and then I take the functor that X represents. So these are adjoint functors. Okay, and they're adjoint functors from the category of topological spaces to the topological spaces. So having a map from X cross something is the same thing as having a map to X, the mapping space with X. All right. So moreover, this is not just they're not just adjoint functors from topological spaces to topological spaces, right? This actually works as continuous maps. So these are actually homeomorphisms. Okay, so this is a mapping space, and this is a mapping space. So this is a topological space, and this is a topological space. And you can actually prove, and I won't, but that these things are isomorphic topological spaces. All right? And so I just kind of want to make a little remark here, is that, so we've shown that there's a bijection. So that's what we essentially did. So there's a bijection. Right? And so so we want to fit this into the framework where the bijective continuous maps are homeomorphisms. So and I don't remember it off the top of my head, and so I can't remember if X needs to be compact or locally compact. But we would need this topological space to be, I think, locally compact, and then either compact. So if they're Hausdorff, is that just enough? I think one of them needs to be compact Hausdorff, but we did this at the very beginning. But this is the type of thing that you want to use to prove this. Okay, so this is kind of the big point, is this adjunction. Okay, so there's other things that we can do, right? So other properties that so kind of extensions of this. So if both X and T are locally compact, then we have two more formulas that are similar to this one. The first formula says that you can move products. Okay, so this is where we're going to use that they're both locally compact. So we go maps from X disjoint union T to Y, right? And so this is going to be homeomorphic to maps from X to Y cross maps from T to Y. Okay, and then the other thing that we're going to have is that that this behaves well on products on the others. So if you have a coproduct here, right, then it breaks up like this. But the other thing we can do is we can do the coproduct on the other side. So we can do Z cross Y, and so this is isomorphic to top XZ cross top XY. Okay, so how do we prove these things? So these will come from general category theory principles, right? So this is a representable functor. So note that top X. So this is one of these HX functors is representable. And then these representable functors preserve limits. And the product is a limit, right? Similarly, this this thing here is co-representable, right? And so that should preserve co-limits, and that's not a co-limit. So, I guess it turns co-limits into limits, right? So it'll turn this product diagram, this coproduct, into a product. Yeah. So that's yeah. So that's all I want to say. I guess the other way is, I guess this is another way to think about it is that this is a contravariant functor, and the contravariant functor will flip. So then we go to the opposite category where products become coproducts, and so and then so yeah, so it should flip the coproducts to products. Okay, that's a little hand wavy, but sorry. All right. So I mean, okay, let me just say it's not hand. So the representable functors preserve limits is not a thing, and then this co-representable functors that they flip the co-limits to limits is not a hand wavy thing. I just felt that wasn't the best description, the best explanation though. Anyway, the other complement that I want to say is that we can do this for pointed spaces. So we can also do this for pointed spaces. And this gives kind of a very fancy perspective of the fundamental group for pointed spaces. Okay, and in this case, so if I'm going to use I'm going to do some abbreviations, right? So we're going to let T be T. So I'm just going to omit the points in the following notation. Okay, so what we're going to have is we have a similar thing. So let's do top. So the exact same thing happens. So I guess this needs to be locally compact Hausdorff. Right? Okay, this thing becomes here then okay, so these are pointed topological spaces, right? And then we have X wedge T, or sorry, smash T, Y. Okay, so all right, so this is in the category of pointed sets. So something to keep in mind here is that so how do we point? So what is the distinguished point here? Y. Okay, so this is really maps here. And then we have the constant function here. So this is the constant function. So we need to pick out a point here. And so this function here. So this is a function from x to y of pointed topological spaces. And what it does is it sends every x to just y naught. Right. So this is how this is how to make how to make mapping spaces. Okay, and what is this thing? So this thing here, so this is the smash product. Okay, and what is the smash product? So you take the product of two spaces, and then you mod out by the wedge. Okay, and so how does this work? So how do you view this as a subset of this? So so again, so what is this thing? So here, so if this is x, and here's x naught, and here's t, and here's t naught. So you identify these two things, and this is x wedge t. Okay, and they're smashed at the. So this is the. So by the way, this thing here. So this is the coproduct. So let me move this up. This is the coproduct in the category of pointed topological spaces. Okay. And so what do I want to say about this? So and this kind of plays the role of the product in for pointed topological spaces. So yeah, so let me just say a little bit about that, and I need to remember how this goes. So we have so how do I view? So we have x's and t's, right? So this is what this is what's an x cross t. Okay, and then we have two things. So we have x's and t naughts. So this is x cross t naught. And then we have x naught cross t. So this is x naught cross t. Right? And then I suppose that the wedge should be then as a subset. So so what's the 2 points that are identified here? That makes sense. So the 2 points that are identified here are so note that in x cross t, the points. So this is just t, right? And so the points x naught, t naught in one copy are identified, and in the other copy they're also identified. Okay, so let's see if I can think of a very particular example where we can actually see this. So let's say we have a torus. So if x is equal to S1. So I didn't like the description of the smash product I gave at the end there. So I'm just going to take a little mulligan here. So an S1 wedge, or S1 smash S1. So this is S1 cross S1 modulo S1 wedge S1. So we haven't really talked about quotients yet, but you can essentially shrink in any topological space. You can shrink a subset to a point. Okay, and so so this thing here is a torus. So this is a torus. Okay, S1 wedge S1. This is this loop and this loop, and they're identified at a point. So it's one-dimensional. So that means that, okay, and so another way of viewing this, there's another way of doing this, is that you could take a square and then you could identify sides like this. Okay, so this side is quotiented with this side, and this side is quotiented with this side. So it's like you've taken the cylinder, okay, or sorry, the torus, and then I've cut it along here first. That gives me, then when you open it up, you get this with these sides identified. Okay, so it can wrap back together. Okay, then you cut it again, right? And if you cut it again, you get the picture that I just showed. Okay, so where these two sides are identified. Okay, so this is kind of the so this is the like fundamental domain picture here, and so in this thing here, when it sits inside here, so we have this loop here, and then we have a loop around, say, the inside. So this is like this, and they meet up at a point. Okay, say on the top right there. Okay, and so one of these cuts, so this cut is like this thing, right? And then this cut is this piece. Okay, so if we were gonna, so smashing, so you know, taking all of this thing and crunching it to a point is the same thing as taking the boundary here and then crunching it to a point. So here, what we can do is, so S1 wedge S1. So this is the same thing as, you know, this square with the boundary identified. Crushed to a point. Right? And so, so this whole thing, everything there is just brought together. And so that thing looks just like a sphere. Right? So this is S2. Okay, so if you take a square and you pinch all the boundary together, or you take a disk and you crush the boundary to a point, then you're going to get S2. Okay, so that I think is a better description of what S1 smash S1 is. A better explanation.